Well, hi, hello, welcome to section number 9. We do not quite have a quorum. We have 6. And ding dong. Again, most lively section, also most late. Love y'all. Love y'all. So, QR code for attendance things. Our molecule today is benzene because lecture 9, she's the main girl, she's the star. It was lovely having one-on-one meetings with y'all. I think I met with everyone in the class except for like 3 people, which is crazy, but also has left me very tired. So I will be catching up on sleep. Game plan for today. So we are going to talk about radicals, which we put off from lecture 8. Then we have EAS reactions and directing effects, which were kind of the bulk of lecture 9 yesterday. Then we are going to go into how to study reactions part 3, the threequel. And then finally, we will end off with a hard synthesis that we're going to do together in the extra challenge problems. One topic I did not have enough time to cram into section today is aromaticity. So just a little brief recap of aromaticity and working through some examples. I've made a YouTube supplemental video. So you can scan this QR code and there'll be like a 10 to 12 minute video that goes over aromaticity. Cool. Without further ado, I guess we can get into it. Any logistical questions before we jump in? Okay, in that case. Radicals. They do weird things, like carbocations. So, starting off, radical stability. The trend for radical stability is the exact same as carbocations. So, think about this. Carbocations, have an empty orbital. We have a deficiency of 2 electrons. Radicals, we have a half-filled orbital. So, we have still a deficiency of electrons. So, anything that can donate electrons and stabilize for carbocation is going to stabilize a radical as well. So that's why we see our tertiary and secondary radicals are more stable than methyl and primary. And then we also have resonance stabilized radicals. So we could draw arrows like this radical, 1 electron goes in. And remember, we show radical, like 1 electron movement with single fishhook arrows. Be very careful and specific about that on exams, because if you do write this arrow for everything, we will have to count off like 5 points. Hate it. Then we can get 1 electron from our pi bond over here, and then put the other electron from the pi bond on the far carbon. And our resonance structure is going to have the pi bond on the other side, and then the radical swapped. So resonance stabilized, you're spreading out that deficiency of electrons among multiple atoms. Okay, well, our general line reaction for radical mechanism that we learned in class was the HBr anti-Markovnikov addition. So normally if we just had HBr, we get the product where we add bromine on the more substituted side. So Markovnikov rule, more electronegative group to the more substituted side. But here, if we add ROOR, which is peroxides, and we add delta or HV, then what we get is our anti-Markovnikov addition, where a more electronegative group, the bromine's added on the less substituted side. So this is one of only 2 reactions that we teach you that is anti-Markovnikov. This and hydroboration oxidation, which we all know are a little mnemonic to remember. We have a little FYI box here that's just talking about the delta or HV, indicating that we're doing radicals. HV is like short for UV light that can start the initial homolyzing of the bond. And then the other thing is ROOR is a stand-in for any compound that has like unstable bonds. And typically unstable sigma bonds are between 2 electronegative elements. So like the oxygen-oxygen sigma bond or the nitrogen-bromine sigma bond. Those are pretty stable, or unstable, sorry, and easy to homolyze. So with that, let's get into the mechanism and talk about why we get our anti-Markovnikov product. So radical reactions in general always have 3 steps, a beginning, middle, and end, if you will. The beginning is initiation. How do we go from no dotty boys to 1 dotty boy? Then propagation. How do we go from some dotty boys to more dotty boys? And then termination. How do we go from some dotty boys to no dotty boys? That's at least my way of thinking of it. Initiation it's going to be the easy points on the exam for a mechanism question, because these are going to be pretty much the same every time of just how do we start off. So these steps you're going to want to get really kind of down cold to where you could just spit it out in 30 seconds. So you start off with the bond that's easy to break, and then when you have heat or UV light, it's going to homolyze. Homo as in same, split off where one electron goes with each of the partners, and we get 2 RO dots. Then RO dot's going to interact with our HBr, and it's going to take the proton with 1 electron, and then the other electron's going to go on the bromine. So we get 1 Br dot. So this is, who would win? A flask full of alkenes trying to do Markovnikov addition, or one dotty boy? And it's the one dotty boy. That's going to make everything anti-Markovnikov. But this isn't a great example. I need to change this, because technically I should make this Br dot is our main girl. Is there a more substituted side of this alkene? No. So bad meme. I'll do better. But this one is homegrown, just like the got going to put a cold one. I did typeset this. So here we are. Okay, so once we have our Br dot, this is our main reactive radical that we have. And so then we can start reacting with the molecule of interest in the propagation steps. Your friends are really disturbed that you chose not to sit with them. But, oh wow. So, propagation, we have our Br dot, we have our alkene, and what we do is we take 1 electron from our pi bond, combining with the Br dot, and it makes a sigma bond to bromine. And then we put 1 electron onto the carbon over here. So now, when we did this, we made a bromine on one side, a radical on the other, and we could have done it the opposite way, right? We could have done the bromine over here and the radical on the end. Which radical is more stable, the secondary one or the primary one? Secondary, same as carbocations. So the big thing is we are forming the more stable intermediate. But let's compare this to the first step if we didn't have radicals, if we just did our normal HBr reaction. So in our normal HBr reaction, the first step, we're grabbing a hydrogen. And then we put the hydrogen over here and we make the more stable carbocation, right? So in both versions, the priority is making the more stable intermediate with the radical or carbocation being in the exact same place. But with the non-radical version, we grab an H first. And with the radical version, we add a Br first. That's why we get our anti-Markovnikov addition here. So I think it's important to see the parallels here between the radicals and the carbocations, and then the difference of why we get anti-Markovnikov just being who reacts first. So once we have this, we have a radical on a carbon here. Then we just need to grab a hydrogen. So another equivalent of HBr, which is going to be really abundant in our solution. It's going to be kind of the solvent or the most abundant species. We are going to take an electron from that, make a sigma bond, and then 1 electron from that sigma bond goes onto a Br. Hey, we went from one dotty boy to another dotty boy. It's going to continue propagating on and on and on. But then this is what gets our product, right? So this is the bread and butter, the most important thing for our radical mechanisms. That being said, there is a termination where we go from dotty boy to no dotty boy, in which case we just combine all the different radical species that we could have. So one way is 2 Br dots coming together to make bromide. Bromide? No, to make dibromide. And then the other one is this radical intermediate could interact with another bromine instead of HBr. Now it's not likely, just because remember, this is our solvent, we have a ton of HBr, but this could happen and we would get this side product. We typically will not ask you to write termination steps. 1, because they're boring. 2, because you've already formed the main product that you're trying to get. So we say don't worry about the termination, but just for future mechanisms, future things that you will see, these are the general 3 phases of a radical mechanism. Yeah.
So even if we don't have to write the termination step, do you still want us to write that a radical bromine comes out of it?
I don't think that we would count off if you didn't mention it, because again, we care about what's the mechanism that generates our product, you know? But I mean, it doesn't hurt. Now, this is the standard version that we taught you. But just like with carbocations, we know that they can do funky things. And so we are going to look at some harder versions of radical mechanisms. And I think you're going to see the harder one on either exam 2 or the final. you definitely will have a mechanism radical question either on exam 2 or on the final. Probably not both. It's kind of like DCC. You'll have a synthesis for DCC on either exam 2 or the final. Now, a big thing that radical reactions can do in a mechanism is they can open rings or form rings. So that's going to be a big thing that we will see. But for these harder radical mechanisms, let's talk about our strategy. So a big thing is number your carbons. So it's just helpful, typically starting with the product, numbering your carbons, and then also try to map the starting materials onto the product and get some anchor points. Once you have things mapped out and numbered, then you can make a list of goals of make and break for bonds. What bonds need you make or break? With that, watch out for hidden hydrogens. Because if I did the radical mechanism here and I wrote my product here, it's easy to see that we made a sigma carbon bromine, right? It's a little sneaky that we also made a sigma carbon hydrogen and we just didn't write it out. So be on the lookout for those. So let's try the process out with this. Okay. Opened up. I'm just going to start numbering. 1, 2, 3, 4, 5, 6, 7. Okay, and now trying to anchor this onto the starting materials. Well, one thing is the first step when our alkene reacted was the alkene went and added the bromine. That was the first step. So, and specifically added on the anti-Markovnikov side of the alkene. So based on that, if this is maybe the less substituted side of our original alkene, because that was the first step, then I'm going to say probably that's my carbon 1 here. That's our anchor point between the starting molecule and the product. Do you buy that so far? Okay. Because the first step of the reaction when the alkene reacts with the radical species is it adds the bromine on the less substituted side. And so based on that, because this is the only reactive part of the molecule when we first start, and we know it's going to grab a bromine, it probably added here. So, okay, if we keep numbering 1, 2, 3, and I think the better numbering is going to be 4, 5, 6, 7 this way around because we want to have a straight chain. We could do like 4, 5, 6, 7, but then that's not going to make as much sense in terms of trying to get to a straight chain. That also okay? So let's make our make and break list. And this is where y'all lead. Tell me a bond that is made or broken in this reaction. So for make or break?
Oh, make.
Both. So we broke the pi, and because we have all these carbons now, I'm going to use numbers instead of CC. I'm going to say we broke the pi 2 to 1 bond. And then we make a pi 2 to 3 bond. Great. What else? Yeah, it's you. Yeah, we need to break the sigma 3, 6. Great. And then Micah, did you have another?
I was gonna say we made the carbon bromine.
Yeah, exactly. Sigma between carbon 1 and bromine. Any other bonds that we made or broke? Did we check for hidden hydrogens? So what's a carbon? Yeah.
The 6 on the first one has 1 hydrogen and then 2 the next one.
Ding dong. Always kind of be on the lookout for that if you're doing one with HBr, because generally speaking, you're going to add an H and a Br. So there we are. So sigma, that's going to be 6 hydrogen. Great. I think that we have our list. So with that in mind, we can start. So first off, we have our initiation steps, which is literally just the regurgitation. So we homolyze. We get 2 RO dots. RO dot interacts with HBr. Bloop. You abstract that proton. ROH plus Br dot. Bless you. And we are ready for propagation. So we have our starting molecule with Br dot. Did that feel very fast? Yes. But that's intentional because it's something that you're going to memorize and get really fast, or you could write in like 15 seconds on the test and then focus on thinking through more of the reaction. Work. Sorry. Oh, sorry. Yeah, there's not enough space between the desk and like the front row of chairs here. Here we are. Okay. So now let's start and do our first step. Well, we already said that the first step of our alkene with a radical here is going and making that sigma bond. Bloop. And one thing to notice is any kind of propagation steps, for the most part, we're going to have 3 arrows, which is kind of different from our mechanisms that we've seen that are non-radical chemistry. Typically, we only have 1 or 2 arrows, but we often will have 3 arrows here. So when we do that, we have a BR that is added here. We have our radical. Okay, so we have accomplished a couple of our goals already. So we made the bond to bromine, and we broke our 1,2 pi bond. Great. So now our make and break list can help guide up where we go next, right? So on this molecule, I'll do my numbering again. 1, 2, 3, 4, 5, 6, 7. What is the most reactive carbon in this species right now? 2. She has the radical. So what goals involve 2? Yeah, pi 2,3 bond. So already we know that this is probably going to fold in, be one of the electrons going to make a pi bond. But then in order to get another electron, we have to break a bond. Well, we only have one other bond that we're trying to break. We're trying to break the 3,6 bond. So we're going to take one electron from that sigma bond to help finish off making our pi bond. And the other electron in the sigma bond is going to go on to carbon 6. So see, when we do our make and break list, it does a lot of the heavy lifting for us. I think otherwise, without it, it's really hard to visualize what's happening or keep track of it. But then with it, it feels much more like a little game. So now our only goal that's left is to add a hydrogen onto carbon 6. So we have our HBr. And we do our little 3 arrows. And suddenly, bada bing, bada bang, we are our product. And if you want to do that step of showing, hey, we made another BR dot, we're going to continue propagating. Started off with one dotty boy, ended with another dotty boy. And then typically we will say in the question, no need to show any termination steps, just because we don't care about that as much. So that is our process here. We've accomplished all of our goals. Did that feel okay-ish so far? But see, already we're doing kind of crazy transformations here. This type of thing we'd never really want to do in a synthesis because there are too many kind of possibilities, and also like we're having to think through a lot of what happens and why. Whereas synthesis, we want reactions that are pretty reliable. So let's try one more. Let's do challenge problem 7 together. What? So, how do we know that this is radicals, other than me putting in the radical section? HV, this is our UV light, so this is our tip-off of radicals. Now, we don't have ROOR anywhere, right? So what is going to be our bond that's going to split homolytically? Well, so the C double bond O, that's in the product here. So for the initial one, the thing that we're looking for, and that's from this little box over here, is bonds between 2 electronegative elements that are sigma bonds. There we go, the ON bond. So our first step, our initiation, these are just going to split open. And because I already know organic chemistry, at least y'all's organic chemistry, I'm just going to abbreviate all the stuff I don't want to write with R. On your P-sets, on exams, please write out the structure. Or use R abbreviations in a much more rigorous way. But I just don't want to write all that, so I'm not. Okay. In the product, I'm trying to map things, and I see, hey, there's this whole ring thing where I would bet a lot of money that this is the same as this. I don't think that we actually messed with any of that in the reaction. So I know my nitrogen and this carbon over here, these are probably a good anchor point. So I'll start numbering my carbons there at that carbon. And then in the product, I'm doing 1, 2, 3, 4, 5, and then the 5 connects to nitrogen. So in the starting materials, if I try to do that, this is probably 2, 3, and that means 4 and 5 have to be these carbons, right? Does it matter which one we call 4, which one we call 5? No, it's symmetric here. So either one that we do, it's not going to matter. Okay, so we're ready to do our make and break list. So this is on y'all. What are we doing? Yeah, so we need to make a pi between carbon 3 and oxygen. What else?
I'll break a CC bond.
Yeah, which CC? So this sigma
I think 3 to 5.
3 to 5, because we still have 3 to 4 connected over here, but we don't have 3 and 5 connected anymore. So this used to be kind of like this. Okay, other ones. Yeah, great. So we have sigma 5n. Anything else to break? Well, I guess we have our initial one, our break, our sigma on. Anything else? Any hidden hydrogens? If there was a hidden hydrogen, where would it come from? Is there any source of hydrogens? No. So we don't have to worry about it here. Okay. So we've accomplished our first goal and the initiation of breaking the ON. So now our reactive species are O and N. So that takes me to these two bonds I'm trying to make, right? Which one do you think we should do? Start with the pi 3O bond or the sigma 5N bond? I think either of them could be potentially reasonable, but I would go first with this one. And the reason why is because we know three-membered rings are strained. And so I think having the radical here right next to the straining ring, it's just going to be faster than this thing going all the way around and attacking. So let's try it. We have our numbers 1, 2, 3, 4, 5. If we are going to fold this electron in and make a double bond, then we need one more electron from another source, from a bond that we are going to break. So we need to break our 3-5 bond. That's where I'm going to get my other electron. And then when we're breaking the 3-5 bond, 3 is what's making the double bond now. So 5 gets a dotty boy. I'll make that look a little nicer. Bless you. Okay, so 1, 2, 3, 4, 5. Okay, with this, we've accomplished all of our goals, but one. Well, but one thing, does this give anyone any pause? Wait, what type of radical is this? Primary, secondary, tertiary? Primary radicals we typically don't think of as very stable, right? Well, in a first step, when you're starting to make radicals, you typically will not make primary radicals in a first step. But it is actually okay to make primary radicals in the middle of a reaction. One way that you can think about this is like the rate limiting step is going to be getting your molecule to react with the radical. But once we have a radical on our molecule, we are in a higher energy space. And so getting to that high energy primary radical is going to be more accessible. It's going to be easier to do than if we were going from a stable neutral molecule, no radicals, to a primary radical. So it is okay in the middle of a reaction. So now all we need to do is make a sigma bond between 5 and N. So, bloop. Some people can get really cute with the arrows and the bond angles. So like sometimes it looks ugly, but then like that's pretty cute. So like, I mean, if you care about making your molecules look cute, we're not going to grade the cuteness of the molecules, but I don't know. And we're done. The whole challenge problem looks scary. 3 steps. Wow.
And there's one radical question on the exam?
Yes, it will either be on exam 2 or the final exam. But on the practice exam, it was on exam 2, and so I'm kind of leaning towards making it exam 2. But we could either do a shorter radical question and like 2 mechanisms on that page, or we can do a harder radical question. I don't know yet. So this is the thing, I haven't written the exam, and also this is my first year like really writing the full exam, and so I have never written a radical question before, so we'll see how it goes. Yeah, this one's pretty good. So we'll see how it goes. We'll see.
Here's my knowledge.
Check for missing hydrogen.
You make it brave the time.
Ding dong. Okay, so that is radicals. Do we feel like we have some tools at least for approaching this question?
Yes.
Work.
Wait, if there's no like HBr, then you don't need to count secret hydrogen.
Yeah, because what's the source of the hydrogen, you know?
HBr, right?
Yeah. Yeah.
Or if there's like a shift.
Yeah, I guess, but
The only 2 things that would indicate it's a radical mechanism is HBr or H.
yeah, so we are either looking for an HV or a delta, and we're looking for peroxides. Yeah.
So like in the P set, it said any peroxide could be on there, so we have to just like memorize that like every time we see it.
Look for just bonds between 2 electronegative elements, and look for delta or HV. This is going to be the giveaway, because on the exam we will definitely include that.
Okay, because if there is a peroxide, it still has to have the delta HB.
Work. EAS reactions. Am I right? So my like little like very short story is I remember learning these reactions with a very distinct like place memory, in that the year was 2016. I was a senior in high school, senior spring. I was doing very poorly in OChem 2, and I said I have to lock in. And it was before we even had the phrase lock in, and so we were just doing that. Wow. But I went to my favorite coffee shop at the time. I went at like 7 a.m. when it opened, and it was shortly after Beyonce's Lemonade came out, and so I just listened to Lemonade on repeat for about 12 hours until they closed, and I just did all of the EAS reactions, and there was another family called the NAS reactions, which we don't teach you. And so I very strongly, every time I see these reactions, think about 6-inch heels. Like the hold up, then on the wind, like the whole album. I really associate with EAS. So that's her vibe in my head. And I thought about teaching it and like correlating each reaction to one of the songs in the album. And I was like, that's too much. That's too much. I don't know. But so the EAS, electrophilic aromatic substitutions. The purpose of these reactions is to add chemical groups onto a benzene. And the problem that's associated with this is benzenes, as we know, are aromatic, and aromatic compounds are what? Stable. Wow. Wow. Yeah, I can't believe that y'all got that. I was gonna do what? Stable, just me, but aromatic compounds are what? Stable. Wow. We don't need a call and response. We're beyond that. You know, we're sophisticated. So, because they are really stable, they're not going to want to go and act as a nucleophile. Like, they're in their own lane. And so in order to get benzene rings to act as a nucleophile, we need stellar electrophiles. We need electrophiles that are not shelf stable. We need electrophiles that can only be formed in situ, like situationally. Like when we pour 2 things into a beaker and they make a really good electrophile. So that is going to be kind of our strategy for EAS reactions. The general mechanism is actually pretty easy. It's just 2 steps where the double bond goes and grabs the good electrophile, And then we have added an electrophile and a hydrogen on here. And then we need to restore aromaticity. So we remove the hydrogen that was already here. I just wrote out this hydrogen. It was here initially. But we've added the electrophile onto that carbon. And then we do a little elimination and we restore aromaticity. So really simple once we have our electrophiles. So let's meet our electrophiles. There are three kind of subfamilies in the EAS reactions. There's halogenation. So if we want to add a bromine or chlorine, we need to form this beast, which is essentially just Br2 or Cl2 associating with a Lewis acid. And then this becomes a really good leaving group. Family 2 are making deactivating acids. So essentially we are boiling benzene in some acid, and then we are able to make these good electrophiles in situ that the nucleophile benzene can go and just attack like this, or attack here and push open. The last family are the Friedel-Crafts, and that's what we're going to kind of zoom in on and talk about a little bit more in terms of how do we add carbons to benzene rings. So we'll talk about it a little bit more, but I do have a reaction web that I made for y'all here that shows all of them. The thing that I think is a little bit tricky is you not only need to memorize the reagents, you also need to know how to make each of these high energy electrophiles, these good electrophiles. And they each have their own like separate mechanism. But once you have the good electrophile, then you're just doing that EAS reaction, the two-step one that's pretty easy. So I think thinking about it as like, okay, at some point I will need to memorize all of these making the electrophiles. And I will also need to remember the reagents that go into it for line reactions. So just a second step. We're going to zoom in, talk about Friedel-Crafts a little bit more. So in the past, when we have taught this course, we have done it with mostly just doing SN1 Friedel-Crafts alkylations. So the SN1 route looks like this. The alkyl chloride, the Cl is going to associate with the Lewis acid, AlCl3. And then the leaving group would leave. So this is the SN1 version over here. And what we get is a carbocation. But we can also do an SN2 route. In the SN2 route, if this is a good like primary carbon, methyl carbon, something that's easy to attack, our nucleophile can come in and just attack here and kick off the leaving group at the same time. And we can do a little SN2 strategy where we are done and we get our benzene, like the nucleophile has been added. And we have the little hydrogen. Bloop, bloop. So thinking about Friedel-Crafts alkylation, we have both SN1, SN2 to think about. So let's look at a couple of examples here. And this is also the thing where, again, I do be changing things. And because I did not clock it in time, you might also notice that these section notes were uploaded this morning at 8:20 a.m., right before my first section at 8:30. So I'm going to redraw these a little bit. So I'm going to kind of erase some things and then draw some new molecules. And I think that it'll kind of talk about it a little bit better. So we're going to make this one instead. And then I'm going to do the same thing over here in the product. So apologies about that. But let's think through this. So if we are trying to do Friedel-Crafts alkylation, we know we're starting with the alkyl halide. And then the question that we should be asking ourselves is, did we do this via SN2 or SN1? So the first step is always going to be we associate with our AlCl3. So I'll go ahead and draw what that looks like, the AlCl3 minus plus here. And now, is this going to be a good candidate for SN1? Like, what kind of carbocation would we make if we did SN1 as a route? We would be making this carbocation, right? Is that a stable carbocation? No. So this is bad at SN1. Okay, what if we tried SN2? So what if we just tried our nucleophile coming and doing a backside attack here?
Yes.
It could happen. It could happen, in which case we would get something that looks like or I deleted a carbon. It's really, really common to delete a carbon. So double check, in your starting material here we have 1, 2, 3, 4 carbons. So if you accidentally draw this and there are only 3 carbons, you have deleted a carbon. That will be a -1 point deduction. I hate it. But I even do it. Like every time, every section, I've been doing this every time I've deleted a carbon. Every time. Learn from the mistakes of your elders. Really, don't let it happen to you. It's more common than you think. So now we have our 4 carbons added, and then here we could get to products. But the thing is, for this SN2 route, this isn't just primary. What's going on here? Well, at the alpha beta position, we have beta branching. So we have sterics here. And this is actually going to be kind of like a fair minus, like between fair and poor. So this is also not going to be good. So I would say if we were trying to make this product here via Friedel-Crafts alkylation, we're not going to have a good time. Like it's going to be a bit of a rough go. So let's think about how we could do this instead and get a higher yield. Well, one thing that we could do is we know we can add carbons to rings with acylation. So if instead of an alkyl halide, we add an acid chloride, we are going to be able to install a carbonyl group here. And we know enough reactions where we can get rid of that carbonyl. So first of all, if we add NaBH4 to a carbonyl, what does it turn the carbonyl into? Alcohol. And then if we have concentrated H2SO4 and an alcohol, then what happens? E1. So now we have a carbon-carbon double bond. And then if we have H2 palladium on carbon, then alkane. So we can get all the way down to an alkyl group through, granted, this is a lot more steps, but it doesn't have to deal with any of the carbocation things. It doesn't have to deal with the steric things. It's a really reliable way. And one thing I want to flag, because sometimes in the problem set, I have not changed everything, mostly because Logan and I just talked about this on like Monday. In the past, when we have taught this, we have said that you can do this in a one-step transformation of just an aryl ketone. You can use H2 palladium on carbon to reduce directly to just an alkane. Now, it only works with aryl ketones, ones that are right by a benzene ring, and it looks kind of weird. But this is the thing, different organic chemistry classes and textbooks disagree on this. Like, the textbook that I learned organic chemistry from includes this as a one-step reaction to do. But then other people are like, actually, that only has good yield if you have like a donating group on it, and like there is more going on. Also, typically in organic chemistry 2 classes, when these reactions are taught, we teach you 2 other ways of reducing aryl ketones. They're called the Clemenson reduction and the Wolff-Kishner. Like, anyway, there are lots of ways to do this, and there are ways that you could even do this one step. We're not going to teach you that. The reason why we do this 3-step is because it's all reactions you've seen before. So even though it feels a little involved, it is a reliable route. So let's see what that would be here. Well, if we are trying to do this in our kind of reliable acylation route, this could have come from this acyl group, and then one we did the NaBH4, MEOH, 2 conc, H2SO4, 3 H2 palladium on carbon. And then how we get to our acid chloride that we add, all we do is cut along the bond. So we could have got to this from a benzene ring with, we put a chlorine where we cut. So again, the whole reason for talking about this more is to just be like, compared to the other reactions, when we're doing Friedel-Crafts alkylation and acylation, there's a little bit more nuance. We have to do a little bit more thinking. Because of that, Friedel-Crafts questions are great, like theory mechanism questions on exams. So let's try this other one here. So if we do this association with AlCl3 minus plus, then is this going to be a good candidate for SN2? So for SN2, it's going to be secondary, but then again, we have the beta branching. So I would say it's going to be pretty poor. And again, this is for SN2, because again, we have the alpha beta branch. Yeah, it's a beta branching essentially means the sterics is not right at the alpha position, but there is sterics next door that slows it down even more.
Wait, why
Yeah.
did you draw a circle like inside the cycle answer?
This is an abbreviated way of drawing the benzene, and it's just faster. Don't do it in mechanisms, but you're allowed to do it in like synthesis, like line reaction. Okay, so if SN2 is not good, what about SN1? Good, fair, poor? Leaving group leave, we make secondary, so fair. So that could be an option. But then what's going to happen?
Move the carbon carbon.
A hydride shift, a rearrangement. And so that's going to make the carbocation here. And so this is going to lead to a product that does not look the way we want it to. So it's going to make blum, blum, blum. Yeah. So all this to say, alkylation, watch out for things like rearrangements, watch out for things like beta branching, sterics. Now, asking the question to alkylate or to acylate, one thing that we can do is we can think backwards. So let's start off with this bottom one. So if we thought backwards on this one, we could cut here, and on the alkylation side, we could make this alkyl halide. Is that going to be a good SN2 option or an SN1 option? So the thing is, SN2 secondary, we think fair. Let's also remember the fact that benzene, bad nucleophile, right? So I would go ahead and say this would probably happen through SN1 because we're secondary fair and benzene's not a great nucleophile. Benzene's also bulky too, so there's a lot of things going on. So SN1, our carbocation would be like this. Is that okay? That's fine. So that one works. But then if we try to think back through the acylation side, then we need to make a carbonyl on that carbon. Is that okay?
This ain't Texas.
Oh, it is 5.
5 carbons on the bond. So this would not work. A Texas carbon. Everything's bigger in Texas. So with that, let's try it with these other strategies as well. So these other examples. So we have, if we want to do alkyl chloride here, we can do the chloride here. And then the acylation, we're thinking about our benzene rings where we put carbonyls here. I know I'm drawing it kind of fast, I'm sorry. So are these two acyl groups okay? Like to put the carbonyl here and then do a reduction? Yeah, we don't have any issues. Again, acylation is pretty straightforward. The only time we can't do it is if we have like a secondary tertiary carbon here. Yeah.
Sorry, I'm still confused. What's the difference between alkylation and acylation?
Acylation, it puts a carbonyl on first. So like Friedel-Crafts acylation is when we go from this to having a version with a carbonyl and carbons added. And that's what the acyl group is.
For instance, what's alkylation?
Alkylation is just straight up adding alkyl group, no carbonyl. Yeah, and like the first step, I didn't show it too much. Over here, we talked about SN1 and SN2 for alkylation. For acylation, we start off with an acid chloride, it associates here. And then you can push down, kick off your leaving group, and you get this, oh, what's she called? I think it's called a carbonylid. Yeah, it's a little weird. But this is what the benzene attacks, and it's a really great electrophile. Yeah.
So for both alkylation and acylation, you start with a benzene,
Mhm.
and then for alkylation, you add the
Alkyl.
AlCl3.
Mm-hmm.
And
Yeah.
and for acylation, what's the?
So acylation, we can go back one step further, and these are acid chlorides. So we could add that acid chloride, or we can add this acid chloride. Over here, for the alkylation side, because acylation we set our options over here, for this side, is this going to do SN1? What would it be SN1 wise for our carbocation?
Would it have no shift?
Well, we wouldn't even make it SN1 because we would have to make a primary carbocation. So not good. SN2, is it a good, fair, or poor?
Good.
We think it's good because primary, but right next door we have beta branching. So again, I would say SN2. So I think here, this is the option where we don't have really a good choice for alkylation. So acylation would be better. This third example, alkylation was clearly the better one because it's the only one possible. But for this first one, this one, we could not do SN1 because we would only have a primary carbocation, but doing SN2, we could do, like, this associates with the AlCl3 minus plus, and then we could do a backside attack really easily because it's just straight chain and it's primary. So this one you could do well either route. Yeah.
I'm sorry, I'm confused what your goal is in alkylation. You start with that entire thing in the middle there, like with the carbon.
So we're thinking backwards. This is the product, and we're asking how could we have made this product from benzene?
Okay, you start with benzene and the thing that you drew.
Yeah, yes, it's this plus benzene, this plus benzene, this plus benzene, and that's what we're evaluating. So these arrows, open arrows, are retrosynthetic arrows, meaning that we're going backwards.
And then the ones on the other side are like,
What if we formed it from Friedel-Crafts acylation instead of
so
alkylation?
it's those two to the.
Yeah.
Wait, so for acylation, first you add the carbonyl, then you mix it with soda carbon, then
Yeah, you do the 3-step reduction.
you do E1, and then you do.
Yes. Again, it's 4 steps this way. In the past, it's been 1 extra step of just reducing it. And that's why this feels a little clunky. Like, this whole section feels a little bit clunky. The big thing I want you to walk away from is thinking about that there are other factors to consider when we are thinking about Friedel-Crafts in terms of sterics, in terms of rearrangements, in terms of whether to alkylate or acylate. But yes, I agree. It's like, wow, we could do a 1-step alkylation or a 4-step acylation. Bless you. Then it's less of a major question, I would say. But with that, I'm a little over the time for the section, again, because this is a little clunkier part of it. So I am going to keep on moving if that's okay. But I can stick around and answer questions for it at the end. So, without further ado. Ooh, not that. Let's do this. So we have just been talking about, up to this point, adding one thing to a benzene ring. But when we have multiple things, it's a little bit weird, a little bit different. So first off, let's talk about our relative nomenclature. So if we have something on our alkene group, I'll call it our R group, then the positions right next to it we call the ortho position. The position opposite is para, and then the ones in the middle are meta. So that depends on wherever our thing is on the benzene ring. So if our thing is over here, then ortho is with it, para is across, meta is in the middle. So it really just depends on whatever two things that we're talking about, since it's this relative naming. So what's the relationship between X and Y? Ortho. What about W and Z?
Meta.
Meta. What about W and Y?
Para.
Para. Great. So relative nomenclature. And then, so revisiting an icon. Benzoic acid is the benzene ring with a carboxylic acid. Benzoic acid. We could make that a peroxybenzoic acid by having an OO peroxide bond. And then if we stick a chlorine, what's the relationship between these two? Meta. Metachloroperoxybenzoic acid. MCPBA.
Oh my god!
I just think she's neat. And now we know her full government name, so we don't have to call her McPBA, MCPBA, or metachloroperoxybenzoic acid.
Wait, is the chloride only hash meta?
Sorry?
Like the chloride is only meta, right?
Yeah.
Because it won't be able to do, like, it won't be able to attach anywhere else because, like, the withdrawal and stuff.
We haven't even gotten to that. This is just naming. Like, the name of this compound is metachloroperoxybenzoic acid, and the meta comes from these are meta to each other.
Oh, okay.
Yeah. And MCPBA was our reagent that makes what functional group? It makes epoxides from alkenes in 1 step. So, we'd love to see it. Yes, and adds sin. Ding dong. Aria on the money. So, So, when we have benzenes where there is something on the benzene, we have to ask ourselves two questions. Question 1, does the thing on the benzene make it easier for the benzene to react or harder for the benzene to react? It's a question of activation. So we'll ask, does it make it faster at doing EAS reactions or slower? Second thing is directing effects. So if there's already one thing on the benzene ring, how is that going to determine where the second thing is added? And for this, we have kind of two big key facts. Number 1, electron donating groups are activating and direct ortho-para. So when we think about this, let's think about why it's activating. In the EAS reaction, is benzene the nucleophile or the electrophile? Nucleophile. Remember, we had to make those high energy electrophiles, and it's a bad nucleophile, right? So if we have an electron donating group that can donate electrons into the ring, especially like via resonance, that makes it a better nucleophile because we have more electron density in the ring. It can go and attack something easier. We're making a higher energy donor. Okay, so that's why it's activating. It's going to be faster towards the second EAS reaction. And then for directing ortho-para, directing effects are controlled by resonance. So if we look at resonance here, when we donate a lone pair into the ring, we essentially get a negative charge that kind of bops around. And specifically, it bops around at the ortho and para positions. So we get that these ortho and para positions have kind of a partial negative charge on it because they have resonance structures where there is a negative. So with that, we say that when this thing is going to go and act as a nucleophile, it's going to add a second thing on. It's directed to the ortho and para position, the OP director. Now, alkanes as well are electron donating, but they don't donate via resonance. What do they donate by?
Conjugation.
The opposite.
Hyperconjugation, the opposite of induction. So hyperconjugation is there. I'm going to lean my electrons over a little bit, and it also is going to direct ortho-para. Now, between ortho and para, some classes are very much about it. It's kind of the case of, for our class, if you want to add it ortho or para, just do that, and it'll be fine. What you can see with some standard examples here is when you have a small R group, like in just methyl, then ortho is going to be favored simply because there are 2 ortho positions and there is 1 para position. And so you get almost a 2/3, 1/3 split here. But when you have a bulky group, like a tert-butyl group, it's going to heavily favor the para position just because of sterics. It's going to be hard to add something right next to a big tert-butyl group. So, key fact 1, electron donating groups activate and ortho-para direct. Key fact number 2, electron withdrawing groups deactivate and are meta-directors. So kind of the opposite. Now, deactivating, it's going to make the ring slower at reacting because she is legit taking electrons out of the ring. And if our ring is supposed to be the nucleophile with electrons that go and attack, when we take electrons out, it makes it slower. So that's the deactivating part. And then we can see with the resonance structures that now the thing we're bouncing around is a positive charge compared to the negative charge up there with the donating. So with that, what we get is kind of cold spots on our molecule. The ortho and para positions have partial positives. So they are not going to be good donors. And so relatively speaking, the meta position is going to be more partial negative relatively. It's not an actual negative charge, but it's simply the absence of a partial positive. And so that's why these sites are going to be more nucleophilic, the meta direction. So it's going to direct the addition of the next thing to the meta position on a ring. Now, we could also, instead of withdrawing via resonance, we could have a positive formal charge or something really electronegative, and this withdrawals via induction. That's the one. Oh my gosh, the parallels. Hyperconjugation for donation. Wow. I mean, there's the classic joke of para-Ls. Yeah. There's also on the memes, orthodox, paradox, metaphysicians. Joke. Also, I love this. If you give benzene trifluoride a nitro group, the children's story we should read to all of our kids in the future. It's just like if you get. Yeah, no. Like it's just kind of brain rot a little bit, but I love it.
Is it brain rot? I don't get it at all.
Wait, it's the mouse.
Yeah, it's like just a play on if you give a mouse a cookie.
No, right. I guess I know the book. I'm just not advanced in chemistry enough to get like.
It just does everything. It does.
Yeah,
It just does whatever.
it does whatever.
All that shit.
Okay, we're gonna pull it back in. So we said withdrawing groups are going to direct meta and deactivate. And there's the idea that when we withdraw electrons from a ring, we slow down EAS reactivity. And so we could actually withdraw electrons so much that we shut down some types of reactions. So nitro groups and typically sulfonic acid groups are so deactivating that they will shut down Friedel-Crafts reactions. So if we wanted to do Friedel-Crafts alkylation or acylation and we have a sulfonic acid or a nitro group on our molecule, we cannot do that. We could still do a bromination, we could still do a chlorination, we could still do another nitro group, something else. But Friedel-Crafts specifically, remember, she's the messy reaction where we have to think about nucleophilicity and SN1, SN2, all the things. She gets shut down. The yield is just very poor. So this is all summarized in a ossified chart for you. Where there's a color code from warm donation to cold tones for deactivators. We see all of our activators are more reactive than benzene, so faster speed of reaction. They're also all orthopair directors. And our deactivators, typically, the strong ones have a lone pair that they can donate in. The moderate ones have a lone pair that they could donate into the ring, but they also have a carbonyl that they could donate into the other direction. So that's kind of split resonance, which means that's not going to be as good of a donor as just if we have a lone pair, nothing else. And then our alkyl groups, these are going to be our weak activators that donate in via hyperconjugation. Then we see that our deactivators here all react more slowly than hydrogen. And then we see that the nitro group, sulfonic acid group, and positive charge on nitrogen are the strongest. Carbonyls next to the ring are moderate deactivators. And our weak deactivators are the halogens. But they are a little weird. So the halogens, they are going to withdraw electrons from the ring via induction. But then they also have resonance where they can donate electrons into the ring. Now, which of these do you think is more substantial? Look at this resonance structure. Is that a stable resonance structure? No. So do you think that overall the halogens do more donation or withdrawing? Withdrawing. It's going to be by far its stronger effect via induction. So that's why we say these are deactivators. They withdraw electrons, they take electrons out of the ring more than they donate it. But our halogens, for directing effects, we said directing effects are controlled by resonance. And so that's why they are the one weird example where normally we have withdrawing groups, meta-directors. Donating groups are ortho-para-directors. But this is the one weird example where these are withdrawing, they are weak deactivators, and they are ortho-para-directors. And to that, I say fluorine, you are the only exception. Chlorine, you are the only exception. Bromine, the only exception. I guess if I say they're all the only exception, maybe halogens, you are the only exception. Ding dong. Thank you. Yeah, maybe if you write a parody song for Organic Chemistry, we can find a way to do some bonus points. I don't know. I don't think so. Hey, I wouldn't be the one approving that, so write to Logan and see. Now, okay, with that, I want to do one more guided example. So a classic type of synthesis problem, and this is typically not going to be our big synthesis question in the exam. This typically is a mini synthesis that we do with like line reactions. It's figuring out if we are adding 3 things to a benzene or 2 things to a benzene, which order should we go in? And it has to do with our directing effects and activation. So with this, we're going to make this ending compound the one with the carbonyl. So that's one other edit to make to it. Again, up until this week, I've only had one typo in the section notes. So we were doing well, and how the mighty have fallen. So with this, there are really 6 possible options, just like probability for like what order we could do all of these in. So let's look at all these 6 routes and see what works and what doesn't. So let's say we added our acyl group first. Does this orthopara direct or meta direct? Meta.
Because it's electron withdrawal.
So she's withdrawing via resonance, meta directing. Good. So to get the bromine in the position that we want, did we add it meta?
No.
No.
No, so that doesn't work. And then this, does the NO2 add meta?
Yeah.
Yeah, so okay, that part works. But then if we add our NO2, NO2 is going to be directing an orthopara or meta to it.
Oh no, orthopara, because it's donating.
No. NO2 is withdrawing. It's our strongest withdrawing group. And remember, her structure looks like this. So she is a nitrogen with a positive charge, really withdrawing. And also she's withdrawing via resonance. Well, wait. Pause. We're doing directing effects. So meta, it's going to direct over here. But then our alkyl halide, or I'm saying weird things, gosh. Our aryl group, that's also directing meta to it. So it's going to direct here, right? Is this where we want to add our bromine? No. So here, our directing effects don't work. Now, you make a good point. We put a nitro group on it. It makes it less reactive. But are we trying to do a Friedel-Crafts after this?
No.
No. So it's okay. We can still do brominations if we have a nitro group on. We just can't do Friedel-Crafts. So maybe let's think about that. If we have a nitro group on first, then could we even do Friedel-Crafts? No. So that's going to kill this, and it's going to kill this. So, and this is because deactivation.
And that's because it's such a strong deactivator.
Yeah, that it shuts down Friedel-Crafts reactivity. It could still do other things.
Wait, if you don't pass, you just add an alpha group or an aryl group, right?
Mm-hmm.
Is SO2H also an electron withdrawing group?
Yeah, they're pretty much at the same level of being super strongly deactivating. Yeah. So now with these, let's say we add our bromine first. Bromine, does it direct orthopara or meta? Orthopara. So with this, is this bromine added orthopara to our is our NO2 added orthopara to the bromine? Yeah. And then here, this would be added para. So like those both work. And then here, on the top one, we're trying to do an acylation after nitro. No. So the last one, we better hope the directing effects work. We said that our bromine over here directs ortho and para to it. So it has ortho and paras taken. And then our acyl group here directs meta to it. So it's going to be directing to the same 2 carbons. Is that what we want? Is that where we want to add our NO2 group?
Yeah.
Yeah. So of the 6 options, only one of them worked to lead us to the product. So when you have problems like this in the problem set on the exam, you don't need to think through all 6 options. Really, the general rule is do your electron donating or withdrawing groups, like the nitro groups things, last if you have to add them, or next to last. And then you can test out one or the other. So like, let's quickly do this first one. So we need to add an acyl group and a chlorine. What is the relationship between them? Meta. Which of those is a meta director, the acyl group or the chlorine? Acyl. So it would make sense that we could add the acyl group first, and then it's meta directing. It's going to direct right here or right here, and then we add the chlorine. Okay, so we just do our reagents for that. So for the Friedel-Crafts acylation, we do the acid chloride, AlCl3, and then for step 2, we do dichloride with AlCl3. And it's a similar process for the others. Do you want to do one more practice?
Yes.
Yeah. I've gone a little bit over time with the alkylation versus acylation, but we will make that work. So we're starting off with our alkyl group already here. Does it direct orthopara or meta? Is it donating or withdrawing? It's donating by what? Hyperconjugation. See why this is going to be your theory question on the exam? Because there's so much to think through. Activating, directing effects, it connects a lot of things. So here we have an ortho-para director. And hey, the two things we added were ortho and para. Cool. So now we can just take a stab in the dark as to which one to do. Do you want to try the nitro group next or the bromo group next? Let's try it. So if we do our bromo group, we are adding the bromine ortho. And then over here, our alkyl group's still going to be directing ortho and para to it. So it's going to direct in these two spots. But in our bromine, it's also an ortho-para director to it, right? So ortho-para to it are going to be this carbon and this carbon. Do you think that we are going to get a majority of one product if we have competing directing effects? No. So this is the thing where, because we have competing directing effects, that's not going to be our preferred route. So if we do the NO2 route first instead, then the alkyl group is going to be directing ortho to it, and then the nitro group is going to direct meta to it. Do you see how they overlap? So we're not going to get a mixture of products, and that's going to be our route that works. And remember, the only thing that we cannot do after we add a nitro group is Friedel-Crafts. So this is going to be just fine and dandy. So we use HNO3 with H2SO4 to add our nitro group, and then we use Br2 FeBr3. My little mnemonic that's really, really basic is Cl is with Al and Br is with Fe. So bruh, I'm gonna lift iron at the gym, bruh, bruh. And then Br, bro, and iron. And then this, I'm thinking, I don't have a good one. I'm all call, better all call Saul. I don't know. All call. Anyway, that mnemonics, here we are. This, you've come to expect it.
And then just to clarify, the reagents you put there for both of them, that's
Just memorizing their memory.
But okay, yeah, just checking it.
Yeah.
From the alkene additions, but these are
These are the EAS. Mm-hmm. Yeah.
okay.
So, no, totally.
I don't.
So now we head into our final chunk, which is thinking through how to study reactions part 3 and doing a synthesis. The exam is coming. Oh no. So, yeah, let's chat for a minute. First of all, we have a historical outline of exam questions. This is what's on the practice exams. You've seen it. And one thing to note here, a lot of reactions, 1. 2, 5 of the 9 questions are at the line reaction or synthesis level. So really make sure that, yes, you need to know the mechanisms, really nail the line reactions in terms of being able to generate the product. Now, exam 1 versus exam 2, they are different challenges. Exam 1, you're learning a bunch of ways to think about molecules. You have all these 3D skills, Newman, Chayers, and all that. And then you also are seeing reactions for the first time. We are really asking you with the first exam, can you see the game that we are starting to play? And honestly, that's something that's hard to see within a week. You went from knowing no reactions to having to do a 6-step synthesis in 9 days. That's crazy. And now that challenge doesn't exist anymore because you all are in this course, this far in, you see the game that we are playing with mechanisms, with synthesis. You might not be good at the game yet, but you know the rules, you know,
On the bench right now.
but you know what is expected of you, and you know the types of information that you have to look for, and you know the pitfalls and the specific skills you have to work. And so exam 2, the challenge is not all these different sub-skills and what game are we playing. The game is we now have 80 reactions. And so it's kind of we need you to learn how to play chess. And you need to learn all 80 different pieces, all the different moves that you can play, so that you can like do the actual chess on the exam. But all this to say, it is a challenge, but it is a different skill from exam 1. So if exam 1 was not your finest moment, you still can do well on exam 2. Like the difficulty comes in a different spot. I know a lot of you are giving me eyes. So let's talk about advice and let's talk about study strategies. So advice number 1, get through the problem set as fast as humanly possible. Like try to just blow through it. And I don't mean just like blow it off, but like get to where you can start thinking about actual studying and not just finishing the problem set. So I would encourage you to try to do that like Saturday, like Sunday, have most of it done. And then Monday, if you want to ask some questions at help room and then submit, sure. But like you should be in study mode Sunday afternoon.
Yeah.
Yes.
Second thing, get down your reaction basics by Sunday or Monday, which is a lot. But the thing is, the rest of the studying that you need to do relies on you knowing those basics of what are the reagents, can we generate the line reaction product, can we do the mechanism. And so this is the like active recall, desert island exercises and things. Those are getting your basics in order. And so work whatever method that you are using and try to have those down by Sunday or Monday so that we can start thinking about, okay, we have the pieces. We know how the pieces move. How do we play chess? How do we do this more complicated thing? So that's the advice. And now that would give you through Monday. So Monday through Thursday, what should your studying be doing? Well, there are a couple of issues that you need to engage with your studying for learning so many reactions. One of them is an issue of tractability or organization. Like if you were just learning or memorizing a list of 80 things, it's going to be really hard to keep on track. So I like to think about compartmentalizing or like organizing these reactions into their reaction families. You've seen that on some of my like reaction summary sheets for a couple of the lectures. But also like this was me starting to brainstorm right for the exam. And literally what I'm doing is I'm analyzing the practice exams from past years of like what came. I'm also thinking about like point breakdown for everything. But then I was also like, okay, what are all my reaction families? And I just sat down. If you want to take a picture of this, you can. It's not in the section notes. Maybe I should include it in the future. But we have about 14 families of reactions. And again, you could do this on your own, like if you want to just go through the lecture notes and check and verify. Thinking about we have to get to know 14 families versus thinking we have to get to know 90-something reactions, this seems a little bit more manageable and a way to chunk it that I think is going to be helpful. It also divides up the reactions into functional groups, which is nice. So that is one thing, the tractability issue. Something that you do needs to engage with organization. Maybe make your own review sheet and kind of organize them, or just study, do your active recall in the families as kind of like modular units. The second thing is the integration issue, which is right now y'all are really good at thinking out lecture 8 mode, lecture 7 mode, lecture 6 mode, just in their own little compartments. And we need to be able to ping pong between all of them. Like one of the synthesis I was trying to write yesterday, I literally was like, how do I get a reaction from every lecture?
What?
No, because we want you to be able to take this and do bigger things. I don't know that one's going to be in there. But I'm going to talk through 3 strategies for how to deal with this integration issue and the studying that you should be doing kind of Monday through Wednesday. So, number 1, nature walks. So for a nature walk, start with a small molecule. So what I might start off with is an alcohol. And then just nature walk, see where you go with it. So maybe I'll turn this into an OTS. And then once I have this, I could do substitution elimination. Maybe I'll try to hit it with a CN. Okay, so what reagents do I need in NaCN? Now, what reactions can I do with nitriles?
You can turn it to a carboxylic.
We can. That's the only thing we can really do. We could reduce it too. So then she's an OH. She's a carboxylic acid.
But now we have infinite opportunity.
Now we can do CAD reactions. And see, it's a way of kind of exploring where to go. And it also starts to get you into a creative space for reactions instead of a fear space. Because most of y'all are in a fear space. Yes. But you can also think, okay, what if I branched and I took this route and I'm just going to write LAH as an abbreviation of lithium aluminum hydride. Yeah. So then in that case, we're at NH2. And then, okay, that's a primary amine. What if I made an imine and I used like a carbonyl and like, boom, and like, again, just see where it goes. And if you think about the question of what functional group can I turn this into, then you are also able to test yourself on reagents to make sure that you can supply those reagents really easily. So that's strategy 1. Strategy 2, do y'all have friends?
No.
Wow. Wow. So specifically friends in the class, what you should do, find a buddy, could be your lab partner, that's at least a person that you've had to interact with. And then with friends in the class, be like, no, y'all would be a great synthesis potluck. What you can do is say, okay, everyone Monday night, write 2 synthesis questions. You can either make them shorter, be like everyone write 2 6-step synthesis, or write longer ones. And bring a blank version where you just have the starting molecule, the product molecule, and then your answer key that you did, and make sure they're on like separate pages. And then you do a little potluck, a little exchange, and you can try them out. Try getting a space that has whiteboards, try working on them. And it's really great because you can't find extra synthesis questions outside of this class.
Yeah.
Because like every class's synthesis relies on its specific set of reactions. And so you're not going to be able to just find more online. The other thing is it gets you more in the creative space of like what type of questions can we ask you, which again I think helps make doing synthesis easier. Then if you're scared of synthesis, you're not going to want to think in that space or do it, and then it's going to be very stressful in the exam, right? The other thing that you can do, be mean. Try to trip up the other person. Try to be like, I bet you can't solve my synthesis, and make it really hard. But the thing, when you are doing that, make sure that your synthesis is correct, because it would be very embarrassing. It would be very embarrassing to be like, this is my hard synthesis, and they're like, well, that doesn't work. Either way, it makes you think a lot more about the reaction, so that's good. The last strategy are reaction webs. So what you do is you take a functional group and you ask, what are all the ways I can make this functional group? What are all the things I can do with it? If we are going to end roughly on time, we need to kind of like circle end and try to go fast with this, okay? So I can either do this reaction webs now and we try to go fast and then we can do the synthesis, or we can skip this and do the synthesis in a more reasonable time. Synthesis? Cool. And the answer key I'll post for this, I'll have versions for this. I am going to do one part with you because it's relevant to the synthesis. Primary amines. What are ways that we can make amines? We can make it from a nitrile, yeah. So we could have like methyl CN, and that carbon right here is going to become this carbon. And then what's the other functional group that we can make it from? An amide. So with this, both of them, we can do it via lithium aluminum hydride. Step 1, 2, H plus workup. Both of these were in lecture 5. And I said it's the only real reactions that you are going to learn that are going to make amines, and specifically primary amines. If we're making a secondary amine, we could only make that from an amide. So when you're doing this, not only testing yourself on reagents, but also writing out the functional groups to ID on the edge, because that's going to help you think of your brainstorming. Once you've made and identified all the ways to make these functional groups and all the things you can do with it, then template it, make a blank version, and then test yourself. Can I think of all the reactions? And again, I think some of these like alcohols would be great to do. And you can do them for almost any functional group. But with that in mind, let's look at a hard synthesis. So, let's look at this one. We start off over here, we get to this in the product, and we are going to be trying to do that in 11 or fewer steps. This is a pretty hard synthesis, I would say. I'm going to give you a couple minutes to start kind of turning your gears thinking about it. In those couple minutes, what I want you to do, identify functional groups, brainstorm reactions that you know with those functional groups a little bit. I want you to do things like count carbons, because it looks like a pretty dramatic transformation happened. Did we add or remove any carbons? And then I want you to think about big goals for the synthesis. What are big things that we either have to add or accomplish or do or change? And see what you can come up with. I don't expect you to have a route. I don't even expect you to have any like reactions yet. Maybe if you have a product and you see, oh, amines, I only know 2 ways of making amines, maybe try to draw the step right before of the amide or the nitrile version to see what it could have come from. So I'm going to give you a couple of minutes to try to do some of that analytical work, and then we will talk through it together. Does anyone need to write this down before I kind of shuffle this off screen?
No. Really quickly go back up to the admin thing.
This? Yeah. So let's talk about some of this analysis. In the starting materials, we only had an alkene. In our product, we had primary amines. Because we had primary amines, we know we really could have only made it from nitrile or amide. So I just drew out those options to help me kind of visualize and see which we could do. Then the other thing is we started off with 6 carbons. We ended in 8 carbons. So with all this, I've come up with 3 big issues that our synthesis has to get through. One, we need to add 2 carbons. So with this, making carbon-carbon bonds is hard. We only know a few ways of doing that. What are some ways? Yeah, we could do like Grignard, like organometallics. What's another way? What? The Wittig. That's a great way of making carbon-carbon bonds, and it makes a double bond already. And then what else? There aren't really many others. The one that's kind of sneaky, you could do an SN2 with cyanide, and that's a carbon nucleophile, right? And because we see that this is one of our options, and we see another goal is we need to add 2 nitrogens and 2 carbons, does that lean you towards the nitrile method or the amide method? Nitrile, because it does 2 of our goals at once. So let's say, hey, this is our route that we want to try. Let's ignore this amide and see if it works out. So our last step, we could do the lithium aluminum hydride with an acid workup.
Wait, could you explain how you decided on that?
Because we both needed to add 2 nitrogens and we needed to add 2 carbons. So those together, to me, suggest if we use a nitrile, we could do 2 birds with 1 stone. We can accomplish both of our goals together. So now, okay, if we are pursuing this strategy, we're thinking about our nitriles here. Breaking open rings. Now, in the past when I've taught this, I have used a name for a reaction that I did not know was inappropriate. So can I tell you about the inappropriate thing that will make you remember it, but I now know it's inappropriate, and so I feel very embarrassed that I used to not think of it. So this reaction, the ozonolysis reaction, I used to call the Lord split me open reaction because I thought that that was a religious experience, like the Lord coming into your life, breaking you open. And then I thought that there were memes online that would use it in inappropriate ways, but I thought it was sincere. I thought it was talking about like evangelicalism in the South. And that's not the case. But ozonolysis is a great reaction for busting open a ring. Great reaction. Because if we have a double bond in a ring, ozonolysis are oxygen scissors coming along and breaking that double bond. And so it's a way that we can go from a ring to a straight chain. So if you ever are in a synthesis and you need to break open a ring, yeah, with alkenes. So we definitely need an alkene in a ring. But ozonolysis should be one of the first things coming to mind when you think about busting open rings. So we have that. Okay. So with this ozonolysis, we need an alkene in the ring. To get an alkene in the ring, what reactions make alkenes?
All that.
Like eliminations make it. So maybe we need like a leaving group on the ring and then we can bust it open. And so it's not really super clear how we can get there yet. But why don't we try to just install a leaving group and see what happens? So one leaving group could be adding a bromine, something. See, like I know that that's not going to 100% solve it. But if we try HBr, initially, the thing that most people will think, Markovnikov, right? But remember, we have to think about carbocations. So we form this carbocation, we're adjacent to a 4-membered strain ring, what happens? It's going to expand the ring. So that's going to make now a 5-carbon ring. Our carbocation's here. Now we have a secondary carbocation adjacent to a tertiary carbon. What happens?
It's gonna rearrange.
Hydride shift. And this already should be sending warning bells off in your head. Because you're like, if I'm having to think about mechanisms on a synthesis, something is generally wrong.
Yeah.
But this is the thing that even if you didn't do this, you could have done this and it would only be a minor deduction. It would only be like a 1-point deduction. And it would get you closer to getting a leaving group on the ring that then you could do like an E2 elimination. So the idea is right. And this is a rare example. You will not have one of these on the test, I don't think. I'm not going to try to write one. So if it is, then it's Logan. Where we are using something with a rearrangement on a test and we're having to think through it. So this is one of the few times rearrangement on a synthesis that we will see, but here we are. But now, do we have a leaving group on a ring? Yeah. So let's try to make a double bond on the ring. Let's do an elimination. What reagent should we do to try to get an elimination over here? Sorry? Sure, we can use any base. I like Naomi. So use your favorite base. And then we need to bust open a ring, so what should we use? Ozonolysis. So now, this ozonolysis, remember, we have 2 flavors. We have O3 with either DMS or H2O2. You could do it with either one. Like, there's probably a way to figure out with either one. I'm just going to use DMS just to try it. So now, let's draw what our products are going to be. So remember, for ozonolysis, we cut down the double bond, and on either of the carbons that we had before, we make sure that there are carbonyls. So initially in our alkene, we had a hydrogen there. So this is an aldehyde with a hydrogen on the end. Okay, so now we've accomplished our second goal. We have broken open the ring. So now let's think about how to get to this nitrile boy here. So nitriles, if we're doing SN2, we needed to attack something that has leaving groups, right? What's your favorite leaving group? Sure. So what I'm going to do is I'm going to be like, okay, before this I need to have a leaving group. Let's do 2 OTSs. Yeah, I think that's fine. Now, the reagent that we need to do to add the SN2 here to add the CN is what?
NaCN.
NaCN, that's it. Okay, so now OTS. OTS is made from what?
TSCL.
Yeah, but what functional group came before? Alcohols, right? Ooh, so this is interesting. So TSCl with pyridine. We need to get from carbonyls to alcohols.
Oh my god.
We can just use sodium borohydride or soft boy.
What's up,
It's
boy?
all coming together.
You could use lithium aluminum hydride, it's just more steps.
Wait, are we still at 7 carbons though? Like, where's the actual one?
So we had 6 initially, 7, 8
Oh.
from the nitrile, and we're done. Like we kind of stumbled into it working backwards.
Wait, where did this sauce come from?
It came from the nitrogen.
It came from the nitriles, the carbon in the nitrile.
Oh,
Each, there we go. Yeah, Gia. From 2 CNs. Like 1, 2, 3, 4, 5, 6. And then the numbers are not going to add up exactly, but this is 1, 2, 3, 4, 5, 6, 7, 8 carbons.
Okay, so you go up.
Yeah, we increase it by 2 carbons. Yeah. So with this, I'm going to kind of wrap it up. It's a hard synthesis, but we started off with our analysis. We started off with our functional groups. We did some retrosynthetic thinking. Then we identified our major issues for the synthesis and our big goals that we had to get through. And that led us to some strategies like ozonolysis, like the SN2 with nitrile. That then lets us start to try to piece it together, and we worked from both ends. You can get credit for steps just at the end. Like if you did not write anything else, this alone would probably be 3 points, which is better than 0 points. Yeah. It can also be the thing of like, you could have kept thinking backwards here, but the only way you can do that thinking and do that brainstorming is if you have those basics down. If you have the brainstorming reaction webs worked. So keep working on those skills. I think y'all are going to get there. But thank you for coming to section. That's all I have, and I'll answer some questions. Yes.